We arrive at our final stop in the hidden electrolytic village for the third and final test of the Chunin exams. Remember, we will always be given instructions to learn and then battle in the arenas for answers to various problems. For this third test, we learned from Roshi, a powerful ninja with skills of earth release techniques that help us understand the stoichiometry of electrolysis. He begins, since charge is flowing through an electrolytic cell and yielding product at the electrodes, it makes sense that the more product is going to form when more charge flows. And this relationship was first determined experimentally in the 1830s by Michael Faraday. So Faraday's law of electrolysis states that the amount of the substance produced at each electrode is directly proportional to the quantity of charge flowing through the electrolytic cell. And each balanced half reaction shows the amount in moles of reactants, the amount of electrons, and the product involved in change. So it contains the information we need to answer such questions as how much material will form from a given quantity of charge, or how much charge is needed to produce a given amount of material. So to fully answer these questions, we must find the charge. Now we cannot measure charge directly, but we can measure current. And current is going to be the charge flowing per unit time. Now the SI unit of a current is the ampere, capital A, and this again is going to be the charge, where it's going to be defined as the charge of 1 coulomb flowing through a conductor in 1 second. Or you can say 1 ampere is equal to 1 capital C for coulomb divided by S for second. Thus, you can rearrange this overall equation and say that the current multiplied by the time in seconds gives the overall charge. So we have our current, meaning our ampere, multiplied by our time in seconds, and we know our ampere is going to be coulomb per second, so it's like we're saying we're taking coulombs per second, multiplied by seconds. Our seconds are going to cancel, so we're left with charge only, which is simply 1 coulomb, and that's exactly what is represented here. Therefore, by measuring the current and the time during which the current flows, we can find the charge, which is going to relate to the overall amount of product. And there is a stoichiometric map we can use to go from our current and time, which is going to be charge, just like we just said, all the way to the mass of a substance in grams. And as you're going to be using different conversion factors as you go along, and thus you're going to be figuring out the stoichiometry of electrolysis. Roshi explains, problems based on Faraday's law often ask you to calculate current, mass of a material, or time. As we said, the electrode half reaction is going to provide the key to solving problems because it relates the mass of product to a certain quantity of charge. So to be able to apply Faraday's law, we can basically follow some steps. The first step is to balance the half reaction that you are given to find electrons per mole of product. Next, you want to use Faraday's constant to find the quantity of charge, because we know Faraday's constant is equal to 9.65 times 10 to the fourth coulombs per mole of electron. And so that's going to allow us to find the quantity of charge per mole of electron. And depending on the question, you are either going to be using molar mass to find charge for a given mass of a product, or you're going to be using the mass of a product in a given current to find time, or vice versa. Let's go ahead and get into a mini example. How long does it take to produce 3 grams of CO2 gas by electrolysis of aqueous NaCl using a power supply with a current of 12 angstroms? So we already know we're dealing with an electrolytic cell. We have electrolysis. It's giving us a power supply because we're dealing with a non-spontaneous redox reaction, right? Now we know we're dealing with an aqueous NaCl solution, but they want us to focus on the production of 3 grams of CO2. And so we need to take our CO2 and produce it. And so you can have an entire list of standard half reactions you are given. And so the half reaction for the production of CO2 tells us that 2 electrons or 2 moles of electrons are going to be lost to form 1 mole of CO2 gas. And we can use that relationship as a conversion factor to put along to our amount of electrons transferred here. Now we continue to apply the steps. So we have balanced the half reaction, that's already given. We already have the moles of electrons and our conversion factor here. We're going to use Faraday's constant to find the quantity of charge. Before we do that, let's go ahead and start right where we're at here. Based on the question, they're starting off with 3 grams of CO2 gas, and they want to tell us or want us to figure out how long it takes to produce that 3 grams of CO2 gas. So what we're going to do is start off with the 3.0 grams here, And then in order for us to get down to utilizing our half reaction information, we have to go from grams to moles. So we're going to start with 3.0 grams of CO2. We're going to use a molar mass as a conversion factor. So for every 1 mole of CO2, you have 70.90 grams of CO2. Now we actually can use our conversion factor we got from our half reaction. Because we've gotten from grams, now we are into moles. And so in order to figure out the amount of electrons transferred, we are going to use our conversion factor. We have moles of CO2 in the numerator here. So we need to have mole of CO2 in the denominator here. So we would get the reciprocal of this conversion factor. So for every 1 mole of CO2, we're going to have 2 moles of electron. Now, we're going to be using Faraday's constant to find the quantity of charge. And so since Faraday's constant is for every 1 mole, and we're going to get coulombs, we can go ahead and multiply by this new conversion factor, and get 1 mole of electrons is going to give us 9.65 times 10 to the 4th coulombs. And so now moles of electrons are going to cancel, and moles of CO2 is going to cancel, and of course grams of CO2 is also going to cancel. We're only left with charge, and we get 8.2 times 10 to the 3 coulomb. Now for the third step, it just depends on the question. They want us to find time, so we'll use the math of the product in the given current to find the time needed, okay? So we know that time is going to equal to our charge divided by our current. You can basically solve for time using this equation here. And so we're going to take our 8.2 times 10 to the 3 coulombs and multiply by our 12 amperes. Of course, we know that amperes is simply going to be coulombs per second, so that's what we have coulombs here. And going to be 12 coulombs and 1 second here. Okay, so of course our coulombs are going to cancel. We're left with our seconds here, and we're going to take our 8.2 times 10 to the 3 and divide it by 12, and we get 6.8 times 10 to the 2 seconds, or approximately 11 minutes. So essentially, we got up to this portion, we're able to get our moles of electrons, and then we use Faraday's constant to figure out our charge we got here. Next, we used our overall understanding of current, charge, and time to solve for time, like the question asked. We could have went further and solved for current, but this question just wanted time. So you can use stoichiometry and this conversion factor relationships to find any component that the question asks. And this is a very kind of convenient mapping of what we're essentially wanting to memorize or get understood. Now, Roshi have given us all the information we can use for this next battle, the final battle. Let's go. Welcome to our third and final battle to test our understanding from Roshi and to fight to become Chunin ninja. We now have Sasuke versus Gaara. So Sasuke is a part of Team 7, so of course our loyalty lies there. We will be applying the relationship among current, time, and amount of substance. So a technician placed a faucet with 0.86 grams of chromium metal by electrolysis of aqueous chromium sulfate, or chromium 3 sulfate. If 12.5 minutes is allowed for the plating, what current is needed? So essentially you're giving us mass of chromium and asking us to get all the way down to current using that same kind of mapping relationship that we're used to. Of course, this is a different look of it, but it's the same information. We can also add the relationship that our current is going to equal to charge divided by the seconds in time, or the time in seconds, excuse me. So whatever time we're getting here, like our 12.5 minutes, we know we're going to have to convert that to seconds based on this overall expression here. And then again, for our charge, we're going to be figuring out that based on the amount of grams of chromium metal that is given. We also need to make sure we write the half reaction for a chromium 3 plus reduction to get the amount of moles of electrons transferred per mole of chromium. And again, that usually is going to be given to you, so you'll see me just write it out here. And then finally, we just need to convert the mass of chromium again needed to the amount of moles of chromium, and then we can use these Faraday's constant to go ahead to find the charge, and then we'll find the current. So let's go ahead and get started. Now for half reactions. Most of the time they will be given to you, and sometimes if they are not, that means it must be easy to be able to figure out what the half reaction is on your own. Okay, so for the chromium half reaction, it's showing us that 3 moles of electrons must be gained to produce 1 mole of chromium solid. Why am I focused on the chromium solid? Because they're telling us that we have the plating of the chromium solid after 12.5 minutes is allowed. And how much of that plating? 0.86 grams. And we're trying to figure out the current. So we're going to start with our 0.86 grams of chromium, and that means we're starting here. And the first conversion factor is going to be the molar mass of chromium straight from the periodic table. So every 52 grams of chromium, I get 1 mole of chromium. And so we're done, and now we're going to have the amount of chromium needed. So automatically going from grams to moles here gives us the amount of chromium. And so grams are going to cancel. Now that we have the amount of our chromium, we are now going to figure out the amount of moles of electrons that are transferred. So for every 1 mole of chromium solid that's formed, we are going to have 3 moles of electrons that were gained based on our half reaction. And so now we have successfully used this conversion factor. And we are at the point we have figured out the amount of moles of electrons that have been transferred. Now we want to get charge. So to get charge, we're going to use our next conversion factor, which is going to be Faraday's constant. It's telling us that 1 mole of electron is going to have 9.65 times 10 to the 4th coulombs of energy. And so now we're here. Once we get this answer and we use this conversion factor, we are now figuring out what our charge is. And so I take my 0.86, multiply by 3, multiply by 9.65 times 10 to the 4th in parentheses. I then divide that number by 52, and that's how I get my 4.8 times 10 to the 3 coulombs. So that is officially my charge here. We're down to this portion. Now to get our current, like the question wants, we're going to use this expression. So we know our amperes is going to equal current divided by the amount of time in seconds. So we're going to take our current, which is our charge, which is 4.8 times 10 to the 3 coulombs, and divided by our time, which is 12.5 minutes. Now we know we need to convert to seconds here because in order to get our amperes or our current, it is going to be coulombs per second. So we are going to, again, get another conversion factor to go from minutes to second here. So we're going to take our 1 minute is equal to 60 seconds, and I go ahead and get rid of minutes here, and I'm left with coulombs per second as my answer, which is equal to amperes. So I take 4.8 times 10 to the 3, divided by 12.5, get an answer, and then divide that by 60. I get 6.4 amperes. You can also say 6.4 coulombs per second. And that's it, folks. We have gotten our answer. So both Sasuke and Gaara put up a big fight, but the outcome is inconclusive. Luckily, as a collective team, we have enough points to pass our Chunin exams. The current fight is complete, and so is our electrochemical ninja journey. Let's head back to the Hidden Chemistry Village, folks. We are back at the Hidden Chemistry Village for rest and ramen. It will be several years before we see some of our Team 7 members again, and the world will be very different. Many missions would have passed, and even some of our most loyal ninjas have been excommunicated. We won't have to wait too long to see the new changes, though, as the adventure continues in Chapter 21, Naruto Nuclear Chemistry, where we battle against Nagato Pain and the Akutsuki. See you there, folks!